the boys for posterity. A couple things I said last review session at ME340 class. I don't think I want the world here. I made that video anonymous, unlisted. All right, so we're talking about a review session. I think it's always a good idea. I always did this when I was about to approach any class, even taking my PhD right before an exam. I'll make a list. Let's make a list.
You're not protecting.
What's that?
You're not protecting anything.
Well, that's a good idea. See, I hit the wrong button on there. There you go. Let's move this thing down. I need this guy to help. Like, it's Friday, right? You say that on any day, but it's Tuesday. Tuesdays are hard. All right, so testable information. All right, so you know that we have an equation sheet, right? So this corresponds to the equation sheet. I meant to print out a bunch for everybody. I guess I could do that, but we already started recording. That'd be a big gap of silence, so I'm not going to do it. But anyway, someone, a helpful person in the class, said, it's all fuzzy. And they showed me the printout, and I'm like, oh, shit, that is fuzzy. So I remade the equation sheet. So if you got a previous equation sheet and you printed it out, by the way, you don't need to print it out I will give you one. So you don't have to bring one. But I'm just letting you know, if you found the equation sheet to be very fuzzy before, I apologize for that. I've cleaned it up. I also added a couple things, moved some things just a little bit, and I might tweak it a little bit more.
Are we using the book for the exam as
No,
well?
no, closed book, just equation sheet. The difference between my approach to 370 is there's so much stuff from tables and things that we do in there that that was my decision years ago. Yeah, because it was just, and the reason why I don't have people make their own equation sheets is just sometimes that's the only things people do to study, to prepare. I know that, and I'm just going to waste their time. And then sometimes they just didn't put the right stuff on their equation sheet, and that just seems, well, that's their own fault. I'm like, well, that's not. And then sometimes people just will go with the micro writing, see how much little bit in it. And then I don't want people to write like worked out problems on their thing. But then when people become like little lawyers, and like, what if I write this? That's not really, and I'm like, F it. You can do an equation sheet, and you can work from there. So testable topics is just a review. All right, so dimensional analysis, which is like the MLT and the FLT, and you got like a little table on the equation sheet on the front page that has all this stuff. And you know the question is like, is this dimensionless? Is this dimensionally consistent? We talked about density, specific gravity, and specific weight of fluids. These are all fluid properties, you know, from like maybe the first and second class. And yeah, ideal gas law. Usually for us, we usually care more about the density than anything else because that's the fluid property that we're looking at when it comes to gases. I want to say. Maybe to recognize that, you know, that gas constant is a constant, so you can put all the other junk on one side, and then like you have two separate states between two gases. You know, you can have, you're changing one thing, how it affects the second state. Speed of sound. Mostly I care about the gases. I don't care about the liquids, but if we did, we need the bulk modulus, which remember is, you know, some of these things require properties, which is on page 2, which was also very fuzzy before, but now it should be much cleaner now. So these are the material properties we'll use. We won't be asking things like stuff that you would need the table in the back of the book for, right? We won't be asking about vapor pressure because we need big tables and we don't want to bother with that. It's not worth it. Viscosity. This is the early viscosity, so this is the definition of viscosity, but most of the time we go for very small little things, and we're going to do an even distribution, so just trying to figure out, kind of get the idea of viscosity, not necessarily the formal definition there. Manometers, to try to go through and be able to figure out when you got like two bodies or maybe atmosphere, you're going through multiple types of liquids. Try to figure out what the pressure difference is between things. Forces on submerged planes. I probably won't be doing any curved ones, so that's good, right? Buoyancy, good old Archimedes. Rigid body motion, probably won't deal with much with it, but you know, it's a thing. We had a homework problem on it. Velocity field, to get the acceleration from the velocity field, we take the material derivative velocity. Streamlines, I think there's a practice equation that has something with this, but it's not going to be Yeah, well, we had homework with it, so it's fair game. Vorticity, irrotational, basically just asking the question, is this velocity field rotational? Maybe get asked, I don't know. Incompressible continuity, the first part of it is for a velocity field, and this is true, but this is the two-dimensional version of it. For a steady flow, if something's steady flow and it's incompressible and it obeys the conservation of mass. We'll see later on where this comes from, but this is, the mini version of that. That's like a little test that you do. But actually, it's a practical thing. This is like the one we do. Like if it's incompressible and conservation of mass, we know that then the volumetric flow is going to be the same. So we could say that this is and this is the inlet and this is the outlet, or if you have multiple inlets, multiple outlets, you could try to predict what the unknown one was. And then lastly, I think stagnation. So these are like the big topics that we've covered. It's a good idea, kind of like think and associate them with different homework problems or different types of problems. And then start looking at problems in the book or problems from this sample exams, which I wish I had more of. I wish I had more problems to try out, but I got some. I think it's good. I kind of gave them away, by the way. It'd be a lot easier for me just to keep these and then use these as my test, right? That would have been the easy thing to do, but I don't seem to do the easy thing. Go ahead.
Is this PowerPoint posted on Blackboard?
No, but it's sort of identical to the equation sheet. So
Okay.
yeah, it basically is the equation sheet. I just decided to go through one at a time to talk to you about it.
All right.
So like this right here, I just put these things together right here, so we could have, and I can save these for you to do because you have them to do, or I could come up with random problems, or we could work through a homework problem. It's up to you. This is a two-way street. I've done my presentation. Now is a communication. We call this a recitation. It's going to be rhyming the whole time.
How many questions are going to be on this stuff?
Wow. You're asking me to predict the future. I have not written the test yet. I was thinking I was going to go for, some of these things are very short. So it's going to be some short, low point thing, not expensive, whatever. Maybe multiple choice. I hate multiple choice. So I say that, and then I probably won't. I'll probably have like just a short, just like a one step. There'll be one step things which aren't going to be worth many points, and probably no more than 3 somewhat longer. So like if I was going to go and predict things, I'm going to go. Actually, I should have taken this off. I think it was like a 10-point problem at one point. But this had multiple steps to it. It's like each one of these things was worth 2 points or something like that. 3 points maybe. That's where it was. This is probably a longer problem. So this would only be like three of them that would take this amount of time. So you get kind of the sense. Like I can't remember. I should have left the little point thing on there, but I didn't want to commit. By the way, these all came from a 50-minute exam, but they're actually from 3 exams. Some of them were covered in all 3 exams, so you can't really tell how long the exam was actually from this right here. But that class was a 50-minute class.
Can you do that problem too?
Sure, absolutely. I'm just leaving it as an option because you could also pick other ones that are similar if you'd like.
Can I queue up a question after that?
Sure, absolutely.
Can we do number 1 from home 3?
Number 1 from homework 3. We have to look it up. Okay. I should have. I never actually printed out any of the homework stuff. So we'll have to look at it. Okay. So let's take a look at this one. This is a viscosity problem, right? So that's some of the hardest parts, I think, of many problems is recognizing what kind of problem it is.
I said 2 for this one.
What was that?
I said the problem for this.
Oh, this one. Oh, that one. Okay, I'm sorry. I didn't understand. Okay, so we had salvage company. The Coast Guard loves salvage. Is attempting to access a sunken ship. I guess that looks like a ship. It's terrible though. Through a 5,000-pound cargo hatch, and it's circular apparently. The cargo hatch is 20 feet by 20 feet. It doesn't make sense. It looks circular. Oh, there's a balloon. I got to. Okay, I was looking at it. And in the position indicated in the drawing, in the blue drawing. What is the diameter of the spherical balloon required to open the cargo hatch? Ignore the weight of the balloon. Okay, that's true. And the friction of the cargo hatch. All right, great. So we need to switch over to the camera here. So how am I going to do that? How did I do that? Oh, I know what, because I had a different I had a different situation at 370. No, we're going to go this way here. We'll figure it out. And that's going to be weird. Can I switch this in the mid-play? No, I can't. I think I have to do the document camera. And if I'm going to do document camera, I need paper. I'm going to go get some paper. So, talk amongst yourselves as we, there you go.
You put on that thing, so I can just like right.
Okay, sure. I appreciate it, thank you. This is available, by the way, on Blackboard.
That's one of your improvements.
So we're not going to run the board. And let's go to him. And let's have a seat. Ooh. You know you're a big Van Halen fan when you're an adult, but you still put a sticker in. You probably have to keep reminding me that to move my camera. Oh, I guess we did this in class. You're already used to that, having to remind me to move my camera.
You could just do it for you.
You could. All right, so even though it might take some time, I like to write these things out and think about them as we're doing it. All right, so that is a rectangular one. I was lying before when I said it was circular. We have a ship lying on the bottom of the ocean. Let's hope everybody was okay and made it out safe. And there's a balloon hanging right here. And let's see, this hinge, we were told was 50 feet below. And this thing's on a 45-degree angle.
Is it possible to refocus it?
I can try.
There you go.
Thank you, I'm sorry. Focus. That's my whole life, trying to focus on things. I don't think we need this 10 feet, to tell you the truth. I think that 10, no, we do, because then we need to know like where the midpoint is of the balloon. That's why we need it. See, I haven't actually worked this out, so I've got to think my way through the thing. I could read, I also could cheat this whole time, so I have my backup, but let's try to not cheat. Cheating's bad, kids. One thing I think you would need to know is the volume. Do you need to know? I think you need to know the volume. Maybe not, because let's see, we're looking for what is the diameter of the spherical balloon. So I think at some point we need to know what the diameter of a balloon is. Yeah, that's going to be, by the way, so we would need to get for a sphere is going to be 4/3 pi r cubed, right? Information we were not given, I think we would need. Other things we need to know is that the hatch is 20 feet by 20 feet, okay? And I think that, okay, with 5,000, this cargo hatch is also 5,000 pounds. That's a lot of pounds.
Actually, not that heavy for a 20 foot by 20 foot steel plate.
Was that?
That's not that heavy for a 20.
Isn't it? I'm trying to think, yeah.
Yeah, I was thinking, yeah, it has to be.
Well, we could do that. We could actually do that because we know what the weight of steel is per inch. Oh, I gotta excuse my phone.
There also usually is some sort of like grid.
Oh yeah, there's all kinds of stiffeners on there too. Yeah, yeah. So we gotta figure out just if it was just a plate, we could just pretend it's a plate. We could find this information out, and we could get easily distracted. How come it's doing this? Oh, okay.
I have a spare calculator if you need it.
No, I couldn't probably even use it anymore. I don't have something happened to my calculator. I guess I have to play it this way. I don't like that version of the calculator. It made it into a different version. I like the vertical one. I'm almost about to go to my office because I'm addicted to this kind of calculator, but I don't like that particular. Can't do Casio. I'm not trying to hurt your
That's
feelings.
right,
HP baby.
Yeah.
Preferences.
12.5 pounds per square foot.
12 point. Or you got 0.284 pounds per cubic inch is what I usually think of the thing. But if you got 20 foot by 20 foot, was how many inches? I go. So let's go back. So you go 20.
That's 240 by 240 inches.
Yeah.
Yeah, I'm gonna have to go get my other calculator because I can't
40 by
I can't freaking do this.
40 by how thick?
That's what, I think that's what we're trying to figure
Maybe
out.
1 inch.
Because we know
Yeah.
the weight and we know the density of steel.
Yes, I think like 1 inch thick is 923 on 923.
So it's that many cubic. It's
5,000.
so you say 5,000 pounds
11 inches.
divided by. I'm
I
sorry.
think it's about
Go 0.28 by 284 pounds per
That's 0.08
cubic inch.
That's 0.086 pounds per cubic inch.
And then you will get a volume right there, right? So I go 5,000. Where the hell did enter go? There you go. 0.284. We divide that out, so you get 1.761 E4. That's cubic inches, right? And so we would divide that by 20 times 12, right? And then square that. Where the hell does square go? I guess I'll just enter and then go times. And then divide. So that means that this thing is about 0.3 inches thick. That's not bad. I mean, that's a heavy freaking plate. A quarter inch is pretty heavy, but still, you're right. They have to have stiffeners. But they should have done themselves. They're in the ballpark at least. But it's a good question, actually. I think honestly, that's the right mindset. Anytime in engineering, you see a number, go, does that make sense? I swear to you, that's one of the most important things. It takes time. It's not don't do it on a test. Then you waste a lot of time on a test. So anyway, okay. So we recognize that this is a submerged surface problem. So I guess we will draw it on here, and we'll superimpose, and we'll find this is our origin, right? So this is O right here, and we look up our equations, and we know that this is going to be the one that's on an angle. So we want to try to use, we're going to use this guy right here and this one right here. And this might be out at sea. Let's see, what did they use? Yes, they went, of course, I'm probably not going to ask about seawater because these Coast Guards are obsessed with it, even though they don't go very far out into it because they're afraid to go too far offshore. They're the knee-deep Navy, but yeah, I know. I went to Mercury Academy. Don't have a little animosity towards them. But if we for seawater, we would know that is an option. And this is U.S. units, so just note this SI right there. So in U.S. units, that's 64 pounds per cubic foot for this specific weight, because we know that we want to use this specific weight for this, right?
Which
So
table is that? 1.4?
it's the top one out of this right here. It's on the second page of the equation sheet. See, I'm trying to model by giving you, showing you as I'm using the equation sheet. So we're going to use these two equations right here. So we'll start out with FR is equal to gamma YC sine of theta A. And while we're at it, maybe I'm going to write down below there. I wish I had more space over here, so I'm going to write over here that YR, whoop, it's not a Y. I was reading R while I was writing right. YR is equal to IXC YCA plus YC. I should probably modify these to match the conventions used in our book. But let's see. The YC, let's start out with this guy right here. It's a good place to start. The YC is going to be the distance to the center from here. Right there, right? So that's like probably the first thing we want to try to find. So we have to do a little bit of figuring out how far away that thing's going to be. So let's figure out where YC is. So okay, we start out with HC. I'll start out with HC, which is going to be this height right here, HC. And HC, okay, so it's going to be 50 feet, but it's going to be minus 1/2 of this. So this is a 20 feet by 20 feet, so it's going to be minus 10 feet. And it doesn't matter if we go sine or cosine, but we should do it the right way. And we'll go sine of 45, all right?
Why is it minus 10?
Because 50 feet is measured to right here by the hinge.
We're going to the bull.
We're going to the centroid of the thing.
Oh, it's
I guess this isn't the hinge. I guess this is the hinge. Sorry, this is the hinge right here. This is where the balloon is attached, and they're trying to lift the thing up, but it doesn't matter. We're going to go to the center of this square hatch.
just the center, but it's at an angle.
It's at an angle. That's why we have this right here. So this dimension that was provided on here went from the surface.
Yeah, no, I understand.
Okay.
That, but like, why would you subtract the height of the balloon?
Because the middle is right there. The middle is higher than where the balloon's
I
attached.
think he's getting at that the 10 foot is the length of the balloon. Like,
Oh, I'm sorry, because this is a 20 by 20 foot thing.
Yeah, so you have to do trig to figure out how.
Oh, let me see.
The 10 foot is not the.
No, the 10 foot. It's just because it's the same. The 10
This-
foot
this is-
half
this-
the
this
plate
is-
length.
This is 10
That's what it
feet
is.
right here.
Yes.
This is 20 feet, but this is 10 feet.
Yes.
Okay.
Okay, but it's not 10 feet up towards the surface. It's 10 feet that way.
That's what the sine 45
Oh,
is.
okay.
Cool.
So it's like that's the 10, and then here's the
Yeah,
10
yeah.
sine 45.
Yeah. It's this length right there that I'm trying to find.
Yeah.
It's weird because it's the same length, but on the picture it's clean.
Yeah. Well, I mean, actually, I didn't do so bad because
Actually, maybe.
tried. I wasn't even thinking about it. So anyway, that comes out to 42.93 feet. I'm about to go to get my real calculator because I'm not going to use it. All right, so now we want YC, which is actually going to be this. So we actually need the hypotenuse instead to get YC, because Y is a variable that's measured along this line.
Oh, that's why I was confused, because I thought that's what you were solving for.
I erased it and then
Okay,
put it back.
Okay.
All right. So I would say for that YC, I would do differently from what she did. I would say I would divide by, I don't know, I guess the sine, yeah, I would divide by the sine. So I go 42.93 divided by the sine of 45. You could do it either which way, and I think you'd end up at this right spot. So it was just the way that I decided. I wanted the depth first, because really that's like the idea of the YC. Really, is that we want to figure out how deep is the center of the thing. Then I'm going to use this to find FR. Right, so I'll get FR. It's going to be equal to the gamma of this is, let's write up here for salt water, 64 pounds per cubic foot. And as some people will memorize that kind of thing. And then the YC is 60.71, and this actually starts to a point up here, pointless, but in there, but that's okay anyway. We take the sine of 45, we just divided by it. Okay, and then the area of this, which is going to be 20 feet by 20 feet. And so we could get an FR equal to, it's going to be like in the millions, so 1.099 e to the 6 pounds. That's a lot. We also, while we're here, we probably want to get the YR. I kind of prefer to do these separately, but I say she because it's my good friend Alicia Garcia, who I can recognize her handwriting. We'll take I, which is rectangle, right? So that's going to be BH cubed over 12. So 12 is the base, 12 is also the height. And we can also go 1/12. What's that?
Nothing, just a lot of 12s.
What's the matter?
It's just a lot of 12s.
That's a lot of 12s. Yeah, you're right. There's a 12, 12, and 12. Probably coming to like something with 12 and no. So let's see. YC is a 60.71. That's the reason. This is the real reason we got it. We didn't actually need it for right here, right? We could have just used HC. It's kind of silly. And then the A is 20 by 20. And then we're going to add to it the 60.71. So for our YR, which is called YP, I think in the other book, we'll see that it's 61.26 feet. And we can just reckon, we could notice these are always going to be pretty close to each other. They're not very far away.
Where are the 2 12s from?
It comes because this thing is 12 by 12. I mean 20 by. You're right. Where'd they come from? You're right. I'm sorry. I just messed up. I don't know where they came from. They were supposed to be 20 by 20. You're absolutely right.
Too many 12s.
Too many 12s. I'm not sure what happened there. Let's pretend like it didn't happen. It was a 20. Thank you so much for asking. It was an excellent question. Thank you for paying attention. All right, let's go. It's time to wake up. It's too late to get a cup of coffee. So we want to use this now. This is all like a setup stuff because really at the heart of this, in many things, is the free body diagram. That's going to be the thing that's going to get us what the tension in that cable needs to be in order to lift up there. And it's going to be the sum of the moments. So let's see. We will draw this free body diagram. And so right there is the hinge. And in any free body diagram, I like to say, hey, guess what we're doing? A free body diagram. Just draw the words in there. And let's put a reaction. We'll call it H, Y, HX, Rix, and Free. They told us this thing was 5,000 pounds, so we put the number on there, right? 5,000. Sometimes you put a W, but and then the force R. This is the center of there, right? But we know that the force is actually going to be perpendicular. Force always perpendicular, so that FR. And we're going to have to figure out these distances here in a second. But we also have this balloon, and maybe we'll put, I guess we'll put the buoyancy force right there. We don't have to put the tension, it's the buoyancy force that's acting on it. Now we got to get the dimensions, and remember that's 20 feet, not 12 feet. What the hell, where did that 12 come from? I don't know, losing it. Okay, so two ways we can always do when we do the sum of the moments, because that's what we're here to do. Sum of the moments about the hinge is equal to 0. Declare what we consider positive is counterclockwise, which is usual. So here, it's not too bad. We have 10 feet. As I was about to say, anytime you do the sum of the moments, you always have two choices, in how you go about figuring out your moment arms when you're at an angle. We could either do find this distance right there, or we could change this force to be only in that direction. Right, so it's always two ways to do it, so whichever way. Let's see what Alicia did. She always uses the square root things and stuff like this. She doesn't like to use cosines and sines. It drives me nuts. All right, but she's a great person. Let's start out with this weight onto here. Well, yeah, I guess we'll do that as a mid-step. So this is negative 5,000. And just from this angle right here, I would say this is a 45 degree, just like everything's a 45 right now. So we could say, well, let's make that the cosine of 45, even though it wouldn't really matter when it's from 45 degrees. And then we're going to say we're going to use the moment arm is 10 feet. Now the next one, this is also going negative because it's going clockwise, and that's 1.099 E6. That's E6. Now here's something we're going to have to be really careful with. We might be tempted to use the YR, but we have to subtract out the distance to the hinge, because that's actually all the way, that's the dimension all the way, like I could draw it up onto this thing, except it's going to get crowded. It's really just a little bit below, right? We can move our YC over here. The YR is right here, YR, right up to there. So we have to figure out really what this dimension is going to be and subtract it out. So I guess I could do that inside over here, or I could do it over here. Let me see. Find a good spot for it. That's not going to crowd everything up. I see what she did. She did that little distance over to the side. So what she decided to do is to call this D right here. So if you following her solution later on, you can kind of see what she had done. So she took D is equal to YR minus 50 times the sine of 45, and then, but let's see in here, minus 20. All right, because that 50 got you to the bottom of the hinge, but now we're also subtracting out that 20, so that this gets us to the distance. That gives us the distance along that diagonal to the hinge. Right, that gets us this distance right here, and this part. But that's so we can subtract that out. Let me put it down below this so I can get it over the side. That gets us 10.55 feet.
Sine would get you that?
Say that again?
Using sine would get you that length.
Let me double check. Oh, I think I might need to, I'm sorry, divide. She's doing a weird thing where she's...
Because that would be like the hypotenuse, right?
Yeah, we're trying to get the hypotenuse, yes. So 50 is the opposite leg, right, to get the depth. But we actually want to get the hypotenuse of the whole thing from here to here. So we would divide 50 by the sine of 45. Is that right? And that gets us that whole length. Then we subtract out 20. That gets us this distance right here.
Oh, so it's to the hinge.
It's to the hinge. Yeah, because this first thing we need to do is to get to the hinge. Then we need to subtract out the hatch. And now this whole thing right here gets us the distance from here to the hinge. And we can subtract that out from YR, and that's going to get us that distance right there.
Okay.
Yeah.
What exactly is YR in our diagram?
YR
Which
is
distance is that?
this distance right here. It is from here
To FR.
to the to where FR needs to be placed, where the center of pressure. It's the difference. There's the center of the centroid, right? That's the YC. But we need a little bit further to where the actual center of pressure is because it's different from the YC.
So,
Why is the center of pressure always off from YC?
It's a great question, and it really goes back to the pressure gradient, the fact that the pressure is getting larger as you go down. So, like like if this is the depth of the water, and we're just taking right here, the average location to find out what the average force is right here, but the average the correct location is usually about down here, like about 1/3 from the bottom.
Right. It's like almost the center of a triangle.
Yes, this is like the center. You can think of this. We call this the pressure prism, and we can almost think of, well, that's the effective like middle of the integration of this right there, right? But this is for one where the top of the water is right there. If that's not the case here, that this thing is underneath right there. So it's almost, if we wanted to keep visualizing it like the other one, it'd be like a trapezoid. So they've already worked out how to work out the math for that for us, and they give us an equation.
Cool.
Instead of having to derive it every time. So that's what we've done, is we've tried to use that to try to figure out this little tiny distance, right? So that is the thing you're asking about, is the difference between those two spots. Yes, sir.
I found another way to find that distance. I just did YR minus YC plus 10.
I think that'll work. I don't know. It sounds right.
Which gives me 10.55.
Okay. If it works, it works.
YC plus 10. YR minus YC plus 10.
yeah, you're right. That makes sense.
And then the last guy over here is what we want to have. It's going to go counterclockwise. This is FB, and I don't know if I'm going to have enough room here. And that really, okay, so once again, we could decide which way that we want to go. Do we want to find the distance perpendicular to YB, or do we want to turn YB into something that's actually perpendicular to the thing? Either way. And once again, she's doing her little crazy things where she takes the square root of 2 thing. So I need to think my way through that. And I think what I would do was to take the cosine once again. So I'm going to go 20 feet times the cosine of 45, and never room left, equals 0. If we do that, I believe we'll get the buoyancy force equal to 822,400 pounds. And now, with that buoyancy force, we can figure out what the volume needs to be. She didn't do that as an in-between step. She just did it all together. We could say, well, we know the buoyancy force has to be equal to the specific weight. Once again, let me see about this guy right here. Let's see the buoyancy force there, specific weight. And the specific weight is 64 pounds per cubic foot. And the volume, as we said up above, was pi over, come on, 4/3.
Would it be 64, or would it be for air? Because the volume is air.
It's going to be the water it displaces, so it's going to be for the salt water. It's a great question. Does that make sense?
Yeah.
We could treat the air like it's, because
Just because won't the balloon expand as it goes higher?
It will compress.
So it will go
Yeah,
down.
it will actually be smaller as it gets higher, right?
No, it'll get bigger.
You get bigger. You're right. Yeah, you get bigger. Yeah.
So you have denser air because it's.
Yeah.
40
Well, I mean, you could try to quantify that, but we generally just gonna go like, okay, that density is not going to be enough to matter. because it's going to be something like 1/100th of the whole thing. So, but you're right. It could. I mean, if we're going around really, really low, we might start to get the ideal gas law involved and that type of thing. But yeah, so we're going to go 4/3 pi r cubed is going to be equal to 822,400.
So we have to find the radius, or do we have to find the volume?
We have to find the diameter. So we get 14.53. Too low yet. Yeah. And so the diameter, I guess we used big D because we already used little d. Big D. 29.1 feet. And what you're saying about the density of the balloon is definitely true. But in the big picture, I think, pretty sure if you went and started doing that, you would see that it probably wouldn't even affect that decimal place, right? It would be like maybe a couple over.
So the question was asking how big the diameter is for the shaft, for the door to start being lifted by the balloon, correct?
Yes, yes.
So I'm just trying to wrap my head around why. So for that case, I'm just trying to understand like the moment like equation for it. Like trying to understand like why U equals 0, because it's in neutrality or.
Because that's at the point it starts to lift it.
Yeah,
Ah.
29.2.
So once it goes over 0, then it's gonna start lifting. It basically 0 is like that point where.
0 is the tipping point where you
Yeah.
exercise it.
Yeah. All right. On the Q, what was I can't remember now. So much time has passed.
3, question 1.
Okay, homework 3, question 1. Let's pull it up. Let's go to Blackboard. Where you at, Blackboard? Courses. Short attention span. Boy, here just can't remember what you just said. Homework 3.
Question 1.
All right. Get rid of you. All right. Got a little bit of a similar thing going on right here. It's me. And so cylinder is partially submerged in water while also being supported by a cable which is wrapped around a pulley and attached to a gate that holds the water. The cylinder is 1 meter in diameter and is suspended 1 meter above the bottom of the body of the water. The 2 meter wide gate, and you need to know the width of the gate, is attached to a frictionless hinge and is supported by a stop located 4 meters above the hinge. Where the cable is also attached. Determine the required mass of the cylinder in kilograms for the gate to begin to open, there's missing a word, when the water level drops to 2.5 meters. So do we want to walk through it, or do we want to work through it, or just talk through it? We have a posted
Honestly,
solution.
like the free-body diagram and the setup is probably most important.
Okay, yeah. So sure. So let's take a look at that. So I just want to see it in front of me, so I can. Come on, baby. There you go. So in our situation, we had a gate like that, the hinge down here at the bottom, and we had a support right there. So we can imagine that there would be a force right there for that, except that we're looking at the instance where it's just about to open up. So at that moment, that force that would have been there, poof, goes away. We have a force from the cable, And we need to find that tension. Now, you might be tempted to include this cable and this guy and then like this right here, right? You might want to do that. But the problem is, right there is our reaction forces that are actually acting on that. And our whole strategy when using statics, when we can use the sum of the moments, is to get rid of stuff we don't want to know. And we don't care about that one right there. So we can't do this. We need to only find that tension. But the good news is, as long as there's not friction in the pulley, that the cable tension has to be the same right here as it is right there. That's good news for us. We also have, the water. We'll draw it as like kind of ghosted in there, right there. Has a we have a depth. That's actually what we're trying to find, but we know it's going to be approximately 2/3 of the way down from the depth of the water. We can that's one approach that we could take, where we have this FR of the water onto this thing.
Can you make the water a little bit darker?
I was trying not to make it look like it's part of the free body diagram.
Oh, okay.
That was my
Okay.
that was my goal,
Okay.
is to not include things on the free body diagram that don't belong. One very big pet peeve of mine is instructors teach you sometimes and draw the ground. They little cross hatch like, don't do that. It's free. The ground's not in this picture. We've released it. You can't see a force if it's hidden away. The forces are hidden until you make it free. So don't draw the ground, because the ground is hiding the forces. The big F in the free body diagram. We also, just to really emphasize to ourselves, we have the reaction forces, which I always make R's. They're acting right in there. Did I get everybody? I guess I got everybody. Now, really, the magnitude and location of this is really what we're trying to try to find, so that we could get here. All right. So this distance, and it's appropriate to put the distances onto this thing as well. I think this is 4 feet, or is it meters? We were in meters, weren't we?
Yeah.
So 4. So here we want this distance right here, and we could call it something if we want to. I don't know what I called it. I decided to call it H minus this distance right here. On here I call it H minus Y R.
I think they gave us H, is that right?
No, we're looking to find H. So what we could do separately on this is, in terms of our solution strategy, was to, I almost wish I had drawn out the problem here, so let me redraw out the problem. Okay. Just a little bit so we can think our way through the thing. So we have the cylinder. And here's the ground, and here's the stop, and here's the water. And it wasn't submerged all the way, was it?
No, it was like halfway or something. I mean, you were trying to kind of figure out.
Yeah. So this, we call this like Y1. So we had the diameter right here of the thing. We could do the free body diagram of the cylinder itself.
Oh, shit.
So we could, with some things, it's just a good habit to do. You might be able to get away without making a free body diagram, but it's just so many possible instances where you could make a mistake because you thought you could get away without doing the FBD. That it's like a better idea to just do it every time. So we got the buoyancy force on the cylinder right there, and we do the sum of the forces in the y direction is equal to 0. So we said the Ft plus the Fb minus the W equals 0. And so the force of the tension, and now we can find we need the volume, right? Let's see, where's the volume? The volume of the, maybe I should do this buoyancy over to the side. The buoyancy is going to be that right there of the cylinder, which is going to be, this was fresh water, right? So it's 9.8 kilonewtons per cubic meter of specific weight. So I like to use base units, so 9,800 newtons per cubic meter. The area here is pi over 4, diameter is 1. And the amount of depth of this thing was going to be h minus, and then this was also equal to 1, I believe. Oh, I see, I did. Okay, I did this afterwards. Yeah. I see what happened here. Okay. We could put a pin in this and leave this over here, where it's going to be useful to us later. We could leave all of this right here. This is going to be useful to us later. I wasn't reading what my problem was. Go ahead.
To figure out the force of the water.
Yeah. So we have to go backwards. I was starting to think we were going to be able to get the tension first, but it's the FR that we're gonna get. We got to get that in terms of. Yeah, we can't. Oh no. Okay, so we do know I got backwards, right? We do know the height, right? Yeah, because we said h was equal to, Jesus, 2.5 meters. I was thinking of another problem where we were working backwards to get h. Okay, gotcha. So we can get this buoyancy force, can't we?
You have to get the buoyancy force, but we can't figure out the weight of the actual.
Yes, that's right. Thank you.
You know how much water displaces, but we don't know.
Yeah, so this was like 2.5 right here, right? So we don't have to put a full pin into that. So we were able to get what that value is going to be. So 11,545 newtons, right? But here's what we need to come back to this. So let's go back over to this diagram right up there. I guess good spot for this. I'll go over here. FR is going to be equal, as we'll, and say it's going to be, we don't need to use this one over here. We could just go to this side right here because it's not at an angle. And FR is going to be gamma HC times the area. And the gamma is 9,800. The HC is going to be 1/2 the depth, right? Because that's to the center. And they said so it was 2.5 divided by 2. And then the area is going to be the width, which was 2, times the depth, 2.5. And the trap that's here is that the depth, I'll make it a little darker. You might want to go to the 4 feet, right? You'll think of the whole area of the thing. It's not a purposeful trap. It's just kind of like, your mind just kind of goes there. It's the wetted area that matters of the gate, not the full area of the gate, only the part that the water's touching.
So does FR, is that 2/3 of the way down? Is that what
It will, well, no, it's halfway down. The magnitude is based on the centroid.
Okay.
The location is based on the center of pressure. But it will, but that will be, the center of pressure will be 2/3 of the way down.
Yeah, okay.
Yeah, okay. The location of it will be there, but to get the magnitude, you get the centroid, which
Okay.
is the HC.
Okay.
So the center of pressure is consistently 2/3 down.
Yes, it only becomes really difficult if the area is submerged. Then it's going to be like the trapezoid kind of looking thing. But so we don't even want to kind of like play that game too much. Like I left out, there was actually a class that I could have taught where we just
Yeah, because I was
did
panicking about that, because I was like, that's kind of one of the reasons I asked about that question before, is because I was like, looking at that, I was thinking about that class, and I was like,
Yeah, no, it's just, I don't know, it just causes more confusion, I think, than just looking into the thing. Get the value, 61,250 newtons. And then, so the location of it, let's go ahead and go with, pretend like we don't know that it's 2/3, but it's gonna be 2/3. But just as, we use the YR I over YCA, YC. So that location for the YR is going to be equal to IXC over, YCA plus YC. So for this situation, the IC is BH cubed over 12. Let's see if I get the right numbers this time. The base of this is 2 feet wide. The height is 2.5, not 4. That's the trap. I'm going to go 1/12. The y of this is going to be the 2.5 over 2. And the area is going to be 2 times 2.5. And then the YC again is 2.5 over 2. And if you do all of that, you get 1.667, and you're going to go, duh, that's 2/3 of 2.5. But what we really need, right, so we got these two values, and we go back up, maybe we can zoom out, and go to our sum of the moments. Would have been nice. I could make it a little higher. I got a little more space up above it. I was just picking on one of my students in dynamics. He just put the equations anywhere that he wants to on the page. Sometimes it starts to come back up. It's almost like a little spiral. But like, just work one level to get some more paper. But here I am, being a hypocrite. Hypocrisy being a natural and necessary thing in our lives. But anyway, won't go there. Okay, so the FT, the tension is what we were trying to find, and we're going to use it later down there, me having jumped ahead. And so let's go with FR. He's going counterclockwise. We have him 61,250. We got to be careful. Our moment arm is not, what we have found is this guy right here. This is actually the YR, that dimension. And we would prefer to have H minus, so that's 2.5 minus 1.667. Spoiler alert, that's 1/3 of the 2.5. And then we're going to have, the only other forces is going to be the tension, and that acts actually on the 4 feet, right? So that's right there.
I thought the YR would have been like the bottom, like closer to the bottom, like the 1/3 off the bottom, not from the surface of the water.
Excuse me?
Like, it's like the 1/3, isn't it? Like, I'm confused, because like, you said the YR's from the surface down?
Yeah, so like, okay, so here's the water right here, here's the pressure gradient.
Yeah,
So right here is the 2/3, right here's the 1/3.
yeah, that's what, yeah.
Okay. That's what I'm saying, this right here is actually 1/3 of 2.5.
Oh, yeah,
Yeah, okay. So you get the tension, which should have been somewhere down here. Where'd you go? Tension? Hello? It should be the 12,000. I don't see the number. Oh, there it is. 12,000. 12,670 newtons. And now we could bring all of this monkey business back down. Should have done all of this later and grouped it down. Don't do your homework like this, kids, please. It's so hard to follow some of this. It takes me forever.
That's
Forever.
actually like how I do mine.
I know, I got it. But if you could just throw me a bone, man, maybe it'll sit. I don't want to spend as many hours as I am on the things. That's why people gave up. Some people don't give homework anymore. All right, so we have, that's just repetition, so I'll move it up. Okay. So we had FT is 12,670 plus our buoyancy, which we have up above, which is 11,545, and we have that weight, which is what we're trying to find. So we end up getting the weight is equal to 24,306 newtons, and so they asked for the mass. 24,306 and 9.81. So we get 2,478 kilograms. So 2,480 is a good number. I think one of the more challenging kinds of problems for some people is the manometer one. So unless someone has a specific, another request for Tolly.
I was gonna ask to do another problem.
Yeah, the manometry being a challenging thing. We could pick one out of the available problems, or I could.
Like the mystery fluid.
What's that?
Could you do one of those ones with like the mystery fluid in it?
Mystery. Wasn't that the name of SpongeBob's
Seahorse?
seahorse? Yeah.
Oh,
Mystery.
Oh, wow.
That's
Believe
something
me,
else.
guy.
Yeah, that's something else.
Does this one have a mystery? No, this doesn't. No, this wants to know the weight of the piston.
Gear mysteries.
There was a homework problem with it.
Was there?
Yeah.
Let's try and find. I do have this wonderful book here. I was thinking of taking exam problems out of it.
what book is that?
This is the Shams 2500 fluid problems.
Mechanics for dummies.
Yeah, pretty much. Actually, do you know what Shams are? Shams outlines? Oh, I should have brought the other Shams in there. There's a book for almost every course. Sometimes there's multiple books. And you guys, believe it or not, already have access to many of them. You don't have this one. But by the way, I just found it on Googling it. I'm telling you, 2,500 fluid mechanics and hydraulics. There you go.
It looks like the book I look in to find my windshield wipers at Walmart.
Yeah.
Swift books.
So you can go to ResearchGate if you have a thing there. You can buy it on Amazon. You can find a bunch. But that was not available. But Shams Outlines is a very old, but still relevant, sort of like, you can think of them as crib notes or cliff notes. You guys, cliff notes have gone away, haven't they? The yellow little books that people used to, the yellow books. But anyway, with being on campus or doing a VPN from your apartment to campus, if you're on this network, you could just go to Access Engineering, which is part of McGraw-Hill, which is the publisher of many of our books right here. There's a bunch of other books that you can get, but you can go fluid mechanics, and one of the very first things that you could see actually even jumps up in there, Shams outline of fluid mechanics and hydraulics. So there's two different things here. So you have this guy right here.
Professor, can I steal a new equation sheet real quick?
Oh, sure. If you, I only have that one right there, so I could print one out for you if you'd like. But they won't let me print. They won't let me print from here, so I could I can get one later. I'm sorry.
I thought you had like a stack.
No, I don't. I meant to. I was meaning to. Let's see. They also put the other one. There's a Shams outline of fluid mechanics. Actually, so there's the Potter one, and then there's this other guy right here. But if you go to this, you could go and you could find like fluid statics, and you go to manometers, and you get a bunch of solved problems. And spoiler alert, a lot of your professors have these all over the place, and on their shelves, and they take exam problems from them. But you can see that we had a bunch of different solved problems you can often find. So here you go. So you got forces on plane and a curved surface, and you can kind of see you get sort of a similar thing. So more problems equals better. Difficult to memorize all of these things and to write them into your book or whatever right here, but so I'm not too terribly worried about it. But it's also another source, and there's actually a whole separate one by a different guy onto there. But this one is not available. That 2500, at least I don't think so. Let's type in 2500 solved problems. See, it's not jumping up. No, it's not one. But this has a lot of. The Access Engineering has a lot of free books. They don't have any textbooks on there, but they have a lot of free books. Yes, sir.
Do we need to bring our own equation sheet?
No. I'll provide it. I'll provide it. I haven't decided whether I want to, because there's like a little bit on the. I kind of wanted to see. I was thinking about maybe using this little space right there, because I noticed that I had Reynolds transport theorem, which we did talk about, but we don't actually need this for anything right now. But I thought I did include this. I did just recently push this guy. I don't think this version of it. Yeah, I moved a little bit of these around and squished a couple things in there that hadn't been in there more. So so I printed this one out before the most recent one that I'm considering of using for there, which I'll post it like just as soon as I get out of here to up to there. Like I'll call it Rev 2. But I was thinking about maybe I'm just printing out this whole thing and giving you this whole thing. It's just 3 pages instead of 1 page. What the hell? So anyway, let me take a look in my manometer thing, and I'll burn one of these, like a complicated one. No, you asked from mystery fluid. I don't know if I can find one exactly like that. Do you have one in mind that
It was one of your homework problems.
Was it one of my homework problems? Okay.
Yeah, it was like had water, but then there was like a section of like.
Wasn't there also mercury?
Yeah, there was like water, mercury, and some other.
Yeah.
Okay, so that probably was.
Oh, I think there
Was that homework 2?
Yeah.
Yeah, this guy.
Liquid, yeah, that one, problem 3.
Oh, yeah.
Okay, so let me look here.
I think that's a little weird.
It was weird.
It was weird.
I think you also said you forgot to include something or something was a mistake in this question.
Might have been.
He would have fixed it if he did. He goes in and changes the actual right? When you make a mistake, you go in and change the actual document and highlight it.
Yeah. I tried to. That was my goal, was to put them in there. I don't know if I see. I think that there was one in there. I don't see it now. I think I might have said something in there. It says, note that there was a typo in problem 2, asking for the pressure gauge in 1, but that was given. So the question was asked actually. So that was up in there. Right there, I'd accidentally asked for pressure gauge 1 here. That wouldn't make any sense because that was the one that I gave you, right? It was actually 2 that we wanted to find. So this one actually is a closed cylindrical tank with flat ends. And let me draw it quick. Wish I'd printed it out. I'm going to draw it rough. Make sure I draw this the correct up, over, down. Bless you. I guess these look like they're in line with each other. This is not pretty. Looks like a second grade I made. Okay. Maybe an advanced second grade. So I got that going for me. And so this, we're gonna call this A, right there, and we're trying to find that. And see what else was given, was these Y's. So I had Y1, and I think Y2, was that Y2? Oh no, this right there was Y2. And then there was Y3 and Y4. And that was air, and it was water. And we were told that Y1 was equal to 2 feet, and Y2 was equal to 4 feet, Y3 is equal to 1 foot, and Y4 is equal to 0.75 feet. And this mystery liquid was a specific gravity. Is that the one that has that was the one? Or we weren't trying to find the mystery liquid, were we? Okay. We just were given a mystery liquid, which is 0.9 specific gravity. Okay. Come on, move out of the way. Stop. There you go. So, for some reason I have that thing highlighted. I'm wondering what that was about. We're trying to get to A. We're trying to find A, but we're starting here at P. I'll call it P1, which we were given, right? We were given that there's some gauge here that's reading 2 psi. So 2 psi implies 2 psig, so we'll just stick with psig all the way through. So trying to find A, we start at P1 and swim down. So we swim down 2 things. Or, well, let's say if we swim over and then we swim up or down, right? So starting here at this surface right here, we could go over to here. And then we could swim up to right here. So, because we're swimming up, we can go through this, and this is still water. And we're going to go to up a height that's equal to Y3. Well, we were given Y3.
Well, yeah, you're given the height of like, you're gonna have to subtract the pressure that creates.
That's what this is right here.
Yeah.
Okay. And now, you know, some of you might be tempted to go up, but we're going to come right back down the same amount. So we can swim over to right here and then start swimming down to there.
Okay, that's what.
And when we swim down, we go plus.
Wouldn't it just cancel out even if you did do it?
Yes, even if you did do it. It's just an unnecessary step. If you would decide to go up, and then if you decide to go, oh, I'm going to go up another Y4, so you go subtract, and then I would go, ooh, now I have to go down, but that would be this amount.
Okay, I think that's what I did, and I got all confused, because I just added
So,
a bunch of extra.
Is it fine if you put the gamma and then have in like parentheses, you just going through and doing like plus Y3 minus?
Yes,
As you're swimming through, just to make it a little simpler.
yes. And in this case, we would now go Y3 plus Y2. To get to right here. And then we would swim down to right here, and that's going to be some more water, right? So we're swimming down, so that's plus, so we go water, and then I believe that's going to be Y1, right? We haven't used Y1. So we never needed Y4. It's kind of a bastard thing to do.
I think that's what confused me.
Why are we multiplying the
Because remember, there's the specific gravity right here. So this is mystery liquid right here.
So, yeah, okay.
We could do another one of these, and I think that'll help after this one to try to help sort the thing out. So we take the PA, and we're once again using silly US units. So if we got 2 PSI, make sure you go times 144 to get in pounds per square foot. We'll work all the thing through and then divide by 144 again. Because the specific weight of water is 62.4. And Y3 is 1 foot. Then you go plus 62.4 times, bless you, 0.9.
So why are you multiplying the specific weight of water by is that just gravity?
Okay, now the specific weight is going to be pounds per cubic foot.
Yeah.
And then we're multiplying by feet, and we'll get pounds per square foot.
What's SG on?
That's the specific gravity.
Okay.
So that's just a ratio.
Okay.
So you can multiply that either by density or by specific weight, either way, and it'll give you the one for the liquid. It's just using water as a reference.
Oh, okay.
So 1 foot plus 4 feet, I think, if I got that right. And then lastly, 62.4 times our Y1, which is 2 feet. So you get the PA from all of this should be 631.2 pounds per square foot, but nobody uses that. So divide it by 144 inches squared by foot squared. And we end up with like 4.383 PSI. And it says that I didn't answer in PSIG. The problem says to answer in PSIG, so I'm a bad person. I don't know, I'm not a bad person, just make a bunch of mistakes. While you're doing that, let's try to find a good manometer problem. Manometry. Where'd you go?
You don't have to go to absolute pressure.
No, okay, so if you started with absolute pressure, you know, like if this had been, let's see if it's on there. If this had been absolute pressure right here,
Yeah.
this would have been absolute pressure. So most gauges are going to be in gauge, right?
If
So
if you want to take a gauge pressure and turn it into absolute, you have to add atmospheric pressure to it.
yes, exactly right, yeah. 14.7 is usually, and then 101.4 if you really. People are going on nuts with the decimal places. There's some of these are pretty intense. I'm trying to pick one that's going to be. I thought.
See you next week.
See you soon. Yeah, it'll be Monday, right? All right. So I was looking at this last night. I thought I misremembered. I thought I had a couple of really good ones. No, maybe this one right here, and maybe a little challenging. All right. So I'll It's actually just a one-stepper, actually.
Are there any manometer problems on the slide?
Yes.
Professor, I will see you on Thursday.
Yes, sir. Thank you. Glad you could attend. That guy. Boom. We got another one. Was that the only one? Jeez. There we go. There's one from the FE exam. So it's multiple choice too. Oh boy. Love me some multiple choice. Should we do this one?
Alright.
Sure, why not?
Multiple choice.
All right. Got 20
25% chance to get it right. This is the SAT. I hate the SAT where they took points off if you got the wrong answer. So you get like 3 points if you get the right answer, 0 points if you don't answer, but -1 if you get it wrong.
Usually knock off
Which is
two
cruel.
answers that
Which is
are probably not correct.
Cruel though. It's cruel because my desire to answer no matter what is too strong to resist.
I don't know if they still do that. I know they used to, but I don't think they
I might have got into a better school.
Just pick C every time.
Just pick C every time.
Just pick C every time, the entire
Yeah.
year.
I have witnessed where I give this some. I don't want to go off a tangent. I'm sorry. All right, so in open where people have gotten like 2 right out of 29, and I'm like, if you just pick C, you would have got more right. And, yeah. Don't try that. If I give you one of these diagnostic exams where I'm trying to see what you know before the beginning of class, like you don't get actually get that grade. It's just a measurement, right? To see where you stand. And people get like 2 right out of 29. I don't want to pick on people if that's happened to you, but it is like cool. An open water manometer is used to measure the pressure in a tank. The tank is half filled with 5,000 kilograms of a liquid chemical that is not miscible in water.
50,000.
Was that?
You said 5,000, 50,000.
50,000. Well, it's 10 amongst friends. The manometer tube is filled with liquid chemical. What is the pressure in the tank relative to the atmospheric pressure, right? So I suppose they're asking for the pressure that's inside this little piece right here. So they're saying there's chemical here, and then there is water right there. So let me.
Oh, that reminds me. So with problems with manometers where we have a cylindrical tank where it has like a curved top, we have to take that radius into account because
No, it's a diversion.
oh, okay.
Because
We had one of those homework problems. I think it was homework 2 where the gauge was like kind of in the side of like around.
for the gases, it
We're
doesn't
given
matter.
a radius. Do we have to take that?
I know. I'm just following the footsteps of the jerks that came before me. So I don't intentionally try to be a jerk. It just comes naturally.
I think I did it and I didn't take into account the radius, but it just threw me off of that.
Yeah, well, I mean, amongst the reasoning for doing something along those lines, aside from the diversionary thing, is also to try to get closer and simulate life where we have often we're given too much information or not enough information to solve the problem. So there's a certain amount of hoop jumping, is how I think of it, in the training of all of us from kindergarten through 12th grade and even freshman year, where you just do this thing that I tell you to do, and I will just put numbers into it, and I will go move to the next class. But then, like, you go out in the real world, and people say, "Here's a problem." Like, okay, where is the book that tells me exactly how to do that? And like, oh no, you got to actually think. So at some point, we have to kind of like start getting, get you off of that kind of mindset.
And you have to know what you need.
You have to actually know you have to look at a problem, recognize its nature. What is actually going on here? Like, and try to even pull yourself away from which equation should I use? Not even think of it in those terms. Like, which ideas should I use as I approach the problem? But anyway, let's see. So I'm not even sure where this thing is on the tank, but let's try. We didn't even need to know this dimension of the tank. Oh, I guess maybe we did. Okay, so for this problem, I think we need to know the density. Yeah, that's why they're doing this. I see here. We know the dimensions of this tank, and we know what the mass of the stuff inside, right? So I wasn't reading carefully enough. So that 50,000 kilograms, we need to know the volume of a spherical, this end thing. Boy. Don't know that off the top of my head, that's 10 meters
and that this is got a radius of 2 meters. But we just recently said that the volume of a sphere, right?
You can just take two half, you can just take.
Yeah, because you could say that's a sphere and that's a sphere right to there,
That's a cylinder.
right? And then the middle is a cylinder, so we could do that, right? So we know that's 4/3 pi r cubed.
What would you even call that shape?
This guy, I don't know, looks a big pill. It's a capsule,
Capsule.
a rounded end cylindrical tank, whatever. So this too is 2 meters, so we know that's a sphere right there. So we could get the total here is going to be
Whether it's pi r cubed.
pi. Well, let's start with the pi r squared times the length. That's the cylinder plus the 4/3 pi r cubed. So I don't have my calculator with me, but that's going to be, so you guys can be my calculator for me. And so that's going to be 2 here and 2 here, so that would be 6. And then the 4/3 pi, and then 2 cubed. And while I'm over here, I'll maybe get rid of him so I can keep the space, use the space the right way.
92.15.
92.15 cubic meters. So we can get the density. Do we want the density? We might want a specific weight. So let's get the specific weight of the liquid is going to be that 50,000 divided by our 92.15, but let's multiply by 9.81.
Actually, it wouldn't be, because the tank's not completely full.
Oh yeah, thank you. Thank you. It's half full, right?
So is this. I don't have the problem, so is it half full?
Yes, it's half full.
Okay.
It looks half full. It looks over.
Ooh.
Because if you look at like the radius.
You're looking. Yeah, I'm with you. I'm with you. I think we're gonna have to
Take good word for it.
take it like.
Where is it?
It's literally drawn.
But also in the dimension-y part, it doesn't say.
Doesn't say what it is.
It does say half filled, though.
It does. Yes, yeah. Tank is half filled.
Really bad drawing.
That's a terrible drawing. That's why I don't know. Must have been made by a Coast Guard person. They're terrible at writing wrong problems. To get a degree at Merchant Marine Academy, you have to get a Coast Guard license, and that's like a 5-day exam that the Coast Guard administers. All multiple choice problems, written just with this cruel intention of trying to make them all just a little ambiguous.
We have to start a count for when you make fun of the Coast Guard.
You can, but then I actually grew to admire them a lot. And when I worked there, it was a very, very, very nice place to work. But just the nicest people. They're so nice people. They're the nicest people. Let's see. We're gonna need this here in a second. Anybody got this number for me? You just want to hear the stories. Sorry, no, it's not true.
It's 2,661.4216.
Well, you went too fast for me.
2,661.42.
That's good enough. These are newtons per cubic meter, should be. It's a good idea to think of that and compare it to water, right? And water is 9,800.
9,009. Wait, what? The density of water?
The specific weight.
Oh.
That seems like not enough.
99 divided by.
That's a pretty light liquid. So this was at 400 millimeters. We don't need all these dimensions, I'm pretty sure. This was.
I mean,
They didn't say, they said it's some chemical.
No, he's just asking what the least dense liquid is.
Ooh, that's a great question, I don't know.
Looking it up. Or
If you
at
look it
least-
up,
at least
you know,
on the- at
what,
least on the
like I
theory.
like to say to my kids, is your Google broken?
At least in the periodic.
Helium-3.
Was that?
Helium.
Helium-3.
Well, I guess that
That
makes
doesn't
sense.
really exist naturally.
I think
Great.
that's the one where it like flows out of its container because it has some screw.
I suppose whatever would be the least dense gas would also, and it's
Isopentane is the one at room temperature, I think, or 20 degrees C, which is,
Alright, so we did something wrong with our, calculations.
so the pi r squared L, that's for the sides of the tank.
Yeah,
Did we have to do that twice because there's two sides of it?
but see, we had,
I found it.
What?
The volume and the dividing in half are both part of the denominator in there. The two should be on top rather than on the bottom.
I got you. So you're saying, yeah, that should be 2. So that should be 2 up there.
Yes.
Thank you.
Should be 10,645.
yeah.
Thank you. So it isn't that helium that doesn't exist. Okay. So anyway, okay. So now we need to go manometry. So are we? Let's go back to what our goal was. We need to remember what our goal was to find the pressure in the tank. I think, right? It's like, what is the pressure in the tank relative to atmospheric? And once again, that was water. Okay, so what we do is we want to find this pressure right here. So we want to start right here at our atmosphere and swim down. So what we want to do is we want to swim down to right here. So here's the thing we want to find, that P. I guess I'll call it P1. It's got to get a number. Okay, we need a subscript. We'll start with P atmosphere, which is, you know, we could make this PSIG in here so that we could just treat that as 0. And we're going to swim downwards in the water. So here is the specific weight of water, and we're going to swim down. I guess I'll put, I could probably just put numbers in here instead of symbols. I didn't want to just put symbols in there. So we got 9,800 newtons per cubic meter. And then we're going to swim down 0.4. And now we can go across over here. So we don't need that 50. It was
You said 9,800?
9,800, you're right. And then we're going to come up. So we're going to swim minus to get to that. So it's going to go to the 10,645. And we're going to come up 0.225. And if we use this, treat that as 0, which is usually what we do for the thing. We should get 1,407. Oh, wait. My dimensioning might be off somehow. Let me see this again. Oh, I know what happened.
First cylinder.
I'm sorry. That dimension was wrong. Oh, that dimension was to there.
So it's 350.
Yes. Reading the problem, kind of important. Did anybody get this? Or anybody try? No. I can go get my calculator. So I can't use my, I don't know how to change from that silly horizontal version of the thing. Back over. I already found it. No, almost. No, I'm sorry. It says select skin. There you go. All right. So we go 9,800.
Select skin.
That's what it says.
I got 1,034.
I guess my fake calculator. Say again?
1,034.87.
Really?
9,800 times 0.35 minus 10,645 times 0.225. 1,034.
1,034? We did something wrong. What the hell did we do wrong? All right, let's take a look. They're saying they get 108.9. Why is that?
Where did the 9,800 come from?
The 9,800 is the specific weight of water. It's the same thing as they're saying 1,000. Some people use 999. They're going to be off by just a little time. They're going to be off by 10. So let me see they have theirs 918.3 times 9.81 times. All right, so I think some of it came from our volume, I think. Because they have a different.
No, that's not what like, if I calculate that out, that's not what I get, is what they have. I got 1,136 for what the numbers that they have.
Huh. That was nice of them.
Well, actually, no, that's technically giving us in pascals, and they have to convert it to kilopascals. So technically they got 1,407 pascals. So technically I got 1.13 kilopascals.
They're still off by a whole lot.
Yes, it is.
Yeah. I don't want to waste any more of your time, so I'll look and see what just double check it when I'm back in my room. Because I'm not great at this live thinking thing. Let's take a look at another problem. We want to take a look at we have 15, at least 15 left. So what other kind of problem would like to kind of go over? Take a look at what we have here. By the way, don't do a dam. This is a dam problem. We didn't do any dam problem. This is more stuff for civil engineers. They do a weird pressure distribution along the bottom of the thing that we haven't covered, so don't worry about doing a problem like that. We got the sliding so let's see, we haven't really done any like this. Let's do this problem. Okay. So we didn't do any viscosity problems. So a large movable plate is located between two large fixed plates as shown. Two Newtonian fluids. By the way, the Newtonian fluids means that it's a linear viscosity, right? That the viscosity doesn't change with speed, but there are non-Newtonian fluids like cornstarch is one. It's kind of weird because it has these weird behaviors because it depends on velocity. Was that?
They call it leak, I think.
cornstarch and water.
I don't know why, but.
It's because of the Dr. Seuss book.
Is it? Oh, okay.
Okay.
Sounds like a word he'd make, doesn't it?
You're thinking.
Bartholomew and the Oobleck. One of the wordier of Seuss's books. It's
We're gonna get back to that. Determine the magnitude, because we are recording this, just you know. That's a great. It's gonna be a great list. I would fast forward through this. Okay. Determine the magnitude and direction of the shearing stresses that act on the fixed. Why there's a blank between the words? Walls when the moving plate has a velocity of 4 meters per second is shown. Assume that the velocity distribution between the plates is linear. That's okay. So we take a look and we see that we have 6 millimeters between that gap with that kind of viscosity, and we have 3 millimeters between here. And so we have 2 fixed plates, and we have that guy that's moving in the middle. All right. So let me get a blank page and see what's going on with that guy. Boom. Not him. There, yep. Okay. So, plate. This one's fixed. Make it look fixed. Plate. Look fixed. And then there's the gap. He's kind of biased towards the bottom. And we are pulling him with at 4 meters per second. And let's see this gap right there and that gap. This is 6 millimeters. This is 3 millimeters. And this guy has a mu of 0.02 Newton seconds per meter squared. And he's got a mu of 0.01 Newton seconds per meter squared. And we're trying to find, what are we trying to find? Determine the magnitude and direction of the shearing stresses. So we find, boom, that are acting on the fixed plate. All right, okay, so we don't know anything about the width of this, so we're okay. The main equation that we want to use here is mu is related to the velocity and its profile. So when doing this, it's remember the idea in viscosity is associated with the no-slip condition, that the first molecule attached, or first clump, doesn't have to be a molecule, but the little tiny clump is attached and will ride along. So right here, that's fixed and that's fixed, and so we have like a velocity profile that's going to look something along those lines right here. So we could say, let's number this guy, he's number 1, he's number 2. There's only been so many number 1s in history for another SpongeBob reference. And this right here, because we're going to assume it's a linear thing, we could also say that it's going to be the velocity, which we'll call this guy here u, and then the gap, which we could call anything we want to call it. They called it b. Right, so we'll say that this is B1 and this is B2. Has the same velocity in there. So it's a boring problem when I see the answer to it. Bah, you're lame. What's that?
Is the answer 1?
No, the answer they end up being the same shear stresses on the top and the bottom of the thing. But I would, just to be able to understand what's going on here, I would make an FBD. Always good to make an FBD. And when I use shear forces on stuff, I like to use the half arrow. that's happening onto there. And there is some type of force that is being placed on there. But we don't know the area of this, so if they have told us maybe the length of the plate and the width of the plate, we would have been okay. But so instead, we're gonna have to do it on a per area basis. So this is gonna be the overall tau, right? So it's per area. So it is a force, but we just have to do it on an area basis. So here's gonna be tau 1, and here's gonna be tau 2. Tau 1 is gonna be mu1 divided by, times u, which is the same velocity for both of them, right? Because it's got to be the same velocity in that plate, divided by the gap. And for whatever reason, they decided to make this, they go, and maybe we want to take a look at the units too while we're in the midst of this, because that's always a really important part of doing any of this. So it's a Newton second per meter squared, and this is a 4 meters per second, and it's divided by, see this is the 1, so it's 0.006 meters. So taking a look at that, that's actually going to, those meters are going to cancel out. That second's going to cancel out. So we're going to get a Newton per meter squared, which is what we would expect when we have a stress, right? A Newton per meter second. And I'm just going to check their numbers because I have trust issues. 4 times and then 0.006 divided. So we get 13.33 newtons per meter squared, and that's what they got too. And then tau 2 is mu2 u over b2. So we get 0.0, where did I write down? 1. We don't need to do the units, we already checked them out. 4, but now divided by 0.003. And this is why I said it was lame, because I look at that and you calculate it out, and you also get 13.33 newtons per meter squared. So, but if we're going to do an FBD on this, we could go the sum of the forces in the x direction equals 0. Assume it's not accelerating, that it's a constant, so we could say that it's 0. And it would just be tau, negative tau 1 minus tau 2 plus this overall tau. So you just get a tau equal to 26.66. Can do that in my head, maybe. 6, 7. Let's do 3 sig figs on. Newtons per meter squared, and they were asking the actual the way it's phrased. It's kind of lame, but the way it was phrased was to say determine the magnitude and direction of the shearing stresses that act on the fixed walls, right? So the actual answer to them are these guys to the original question would be going that way right there. But I think a better question was what would be the necessary force per area to be moving that thing on. That's personally what I would think. But I'm trying to make this lame question into something that maybe makes a little bit more sense.
Why are the stresses moving the other way?
Because the nature of the way that the thing was questioned, it wasn't determine the magnitude and direction of the shearing stresses that act, magic word, on, right? So we had to get read it's the technicality of the thing. Like those are the stresses of the fluids on the plate that are onto the thing. I would think a better one would be to ask what kind of thing would be required to pull this out, pull the thing out. And I think in one of the problems from the old Coast Guard exams, we had a problem like this, and there was also a problem here with the snake that kind of like went along those lines, right? How much force is required to pull these things away. Another type of problem that we haven't covered that I think is worth trying to look through again is this guy right here. I think it's a pretty important one because later on in the semester we have where we do a dimensional analysis to create non-dimensional numbers. And it might seem like sort of a trivial thing, but I think it's sort of one of the basis of a lot of engineering. A lot of engineering, as we will always see, are deriving equations. But that can only take us so far. So a lot of our stuff is empirical. We create tests, and we get data from those tests. And we don't do it randomly, right? We don't, and because we could be very inefficient to do it that way. So non-dimensional numbers are really important to us. And kind of sort of to me at least, it was sort of a very wow kind of like moment when I kind of figured out what we're able to figure a lot of stuff out in this world as engineers, whereas scientists want to figure out the underneath the meaning of stuff, and you just want to get stuff done. We just want to solve. We have like a task we have to achieve, and yeah, it would be nice to find out why the molecules are behaving the way they are, but that would be something we want to know someday. But we still got to get the thing done. So we create a lot of times we run tests, and the tests get too expensive to do them at full size. So we have to scale models to do that. And the only way that we can is to use the idea of non-dimensional numbers and this magical thing called similitude. And the only way to get better at that is to start picking apart what is the nature of the problem, or what is the nature of the equation? Like what are the dimensions that are underneath the thing? So I saw a couple in this book that I thought were kind of interesting, and it actually kind of appeared in a couple other books. I was looking for other examples. So I was like, okay, that would be a pretty good test problem. And I was like, well, let me open up this other book and look for it too. I'm like, people are asking the same problem over and over again. Kind of infuriating. It's right here at the very beginning, so it's like an important thing to be able to do. I'm trying to find it, flipping pages while I talk. And there you go. Where you going, buddy? Come on. Come back to me. Surface tension. I don't care about surface tension, by the way. That's infotainment. Don't care. Oh, there you go. So we have the Stokes. Oh, I don't know what that is. I don't know what that is. The Stokes-Ocean formula for the drag force. There was one. There's also the speed propagation. Let's see. I highlighted these things, so I'm not sure which one we want to try to use. So we could do, by the way, FLT or MLT you can do in either one of these for these problems. Sometimes it's sort of a challenge. I liked which one did I like last night? So I was looking through here. Let me see. Say again?
It's the Stokes-Ocean formula is drag on the sphere at low velocity.
We will come up and do a drag, so that might be something we were looking at. So let's go ahead. Let's go for the Stokes. It's got a good name too. Isn't that the trial about Stokes trial? About the Darwin thing. All right, so let's go to Stokes-Ocean is F is equal to 3 pi mu d. I think it's a d and a v. You kind of need to know. I think d is not dv, but it's d, and I'm not sure. I guess I'm gonna guess that's velocity. It would not make sense if you took the that viscosity times that kind of viscosity. Plus 9 pi over 16, and then density, velocity squared, d squared. Is this a dimensionally consistent equation is the question. And so what we have to do here is first, I guess, break it down, right? So we don't really care about these guys right there. They're sort of they're just constants. So let's take a look at first mu. So let's first do, okay, so first off, F is right here. Let's go FLT first. So F, spoiler alert, I'm guessing that's a force. Yes, it's a force. Force. Mu, that's viscosity, which is dynamic viscosity. And if I haven't mentioned before, I mean, it's not an incredibly important thing right now, but this is dynamic viscosity. And it's the standard one that you would use, right? As they mentioned. So here's our FL minus 2T.
Is there a different symbol for kinematics viscosity?
Yes, this is mu. This is the Greek letter nu, which looks like a special kind of leaning to the side kind of V. Right? He's got the class. All he is they just divide by density.
I think I've seen that.
Yeah, and it's just a shortcut because quite often that's like those two things appear next to each other, so they often will just make it into one thing. And it isn't quite clear, you know, for here, by doing that, what they do is that's an L squared T minus 1, so just to see that's the difference between dynamic and kinematics viscosity. What's really messed up, and we'll talk about more when we get to viscosity, is like in the real world, they don't use these units. They use centistokes and degrees Sable or seconds, other things like there, which are just a practical thing where they take a funnel with a certain volume of fluid and they pour it through and then they measure the time it takes to go through the funnel. And so you'll see that's just it's an empirical way of getting the thing. Then they're not using viscosity for the calculations. They're just comparing one thing to another thing. So anyway, so this guy in the FLT is going to be the FL minus 2T. The D is, I believe, is going to be L. I could look at it, right? It was right in front of me at some point. Oh, it's right over there. This one. It's the L. And then this V, that should be LT minus 1, right? Velocity. So that's like the first part of this we need to look at. And then when we look at the second part of it, we're going to have density, which is a little weird sometimes to see it in the FLT because we have it makes a lot more sense in the MLT than it does in the FLT. You could convert them to yourself if you wanted to, just using F equals MA as an idea, and you can convert them. And then let's see, this velocity squared, so we're going to LT times T minus 2 right here, and then you're going to L2 right there. So there's two things right there to take a look at. So first off, let's see. We can. Yep, those L's goes away. Those L's go. Yeah.
Is the rest of this recording going to be posted on?
Yes. Yeah. As soon as I can. Yeah. Thank you for coming.
I'll see you Monday.
I'll see you Monday too. Thank you. Have a great weekend.
You too.
So we have the times that cancel out. So we go, yep, that one, check mark. And then we see, okay, there's an L2 squared and L squared. We got rid of the L's. And then we see we got rid of the T's. And so that's check mark, say yay. What's that? Force. So we got the force over here, which is an interesting thing because in the MLT system, that's an mass, length, T to the minus 2. But that makes sense. Mass times kilograms, meters per second squared, or slugs, feet per second squared, right? This is just F equals ma, mass times acceleration. So M, L2, T. No, not 2. Sorry. That's the trouble with this thing. You can really jump down to the next guy down. Just be a little careful of that. Minus 2. So mu is going to be in this system is M plus 1. So M L minus 1 T minus 1. And trust me when I say this is going to be a useful thing later on in the semester. So it's worth looking at it right now. The diameter, well, that's still gonna be L no matter what. And this is still gonna be L T minus 1 no matter what, right? So the F's and the M, the M's don't matter here. And then for density, that's ML minus 3. You can just kind of do that in your head. And then we also have L2 T minus 2 for the velocity squared, and then that's still L2. So I'm a little nervous here. I'm looking at this. I'm okay with these guys.
Should just be.
Oh, I got you. Okay, boom. Gets one of these. All right. Oh no, I didn't. I crossed these out and I shouldn't have. My bad.
Oh, yeah, would it be? I got to do
Minus 2, right? So that's going to be good. We're golden, right? So this ends up being ML T minus 2, which matches with that. And then here, checking out that guy, and then one of those. And yes, sure enough, M L T minus 2. Right, boom, boom. All right. I'm just suggesting that this is a good thing to do. It's a quick problem, simple one, and just something to make sure that you can kind of think your way through and look through, because it's
And we'll probably have something similar to this on these soon.
yeah, it will be not many points, but just something to want to look at. It's just consider, I can't ask every single thing on here. I wouldn't ask every single thing on there. But there's a certain amount of base knowledge that we want to be able to make sure that we're catching up on. And as my philosophy on exams are that the inherent thing is just like kind of just measure. Hey, are we keeping up with where we want to be? And okay, so I think I'm done at 11:09. I hope it's been useful. I'm sorry about the stammering around on a couple of them. I try to be prepared as I can, and this is,
This was helpful.
okay, good. I'm hopefully helpful. And I don't know if the video is going to be the best watch in the world, and maybe we won't make it public.
It'll be entertaining.
It'll be an instant classic.